We're going to consider angular rates of change using the chain rule in this video, and we're going to look at some of the aspects via example. And we have this example I found, and surveyor with a theodolite. If you don't know what a theodolite means, it doesn't really matter. It's a device that surveyors use for measurement. So surveyor with a theodolite at the top of a cliff, it's 120 meters above the water. It observes a boat. That boat is moving away from him at an angle of depression of 35 degrees. And that angle of depression is increasing. Now there's a flaw in this question. It's actually, I'll show you in a minute, it's actually decreasing. Okay, at 20 degrees per minute. Find the speed of the boat in kilometers per hour. Now this one comes with a nice little hint. You must have d theta, dt expressed in terms of radians. So angles, when we use calculus, you need to be they're defined in terms of radians. Okay, that's very important. So when you use angles with the derivative like this one in calculus, you need to be in radian mode. Alright, so use radians for such questions. Start by drawing a diagram. So let's put the surveyor here. He's on top of a cliff, so we'll depict the edge of the cliff with a straight line. 120 meters. Now the boat travels on water, so we'll idealize the water as such, straight line, and connect up to find a triangle, because we're trying to use, whoops, the surveyor's now up here, I'm sorry. Doink, got promoted. So basically we're going to try and see if we can use a right angle triangle, because then we'll have some tools, i.e. regular triangle trig. Now we've got angle of depression. It says here 35. So angle of depression is the angle underneath the horizon. So we have a horizon going out there. That would mean that angle there is 35 degrees. And as you can see, if the boat is moving along the water there, it's moving away from him, it says. Okay, that means it's going on the water like that. So that value of x along there is increasing. And that would, if you can imagine that going further and further out, that 35 degrees is decreasing. So it's decreasing negative 20 degrees per minute. Now, for reasons you'll see soon, such a question like this, because of the trig involved, is a little bit easier, in fact, if you consider the complement, this angle in here. So I'm actually going to make that the angle. Now, if we've got a right angle there, that'll actually be 55 degrees, and that will be increasing by 20 degrees per minute. Okay. So I've just used the complement of the given information. Okay, so those two add to 90. Alright, now I'm also, because we have to find the speed of the boat in kilometers per hour, I'm going to change that to kilometers. So 120 meters is 0.12 kilometers, right? Now we have to be very careful with our units in this question, okay? The angular units and also the other units of time and distance. So units, be cautious about those, alright? So we have a rate of change of angle with regards to time. So one of the things we've got is d theta dt. d theta dt, let's work that out. Now I'm also converting the angular rotation there, 20 degrees per minute. 20, remember pi on 180 will convert your degrees to radians, okay, from previous work, and that would be 20 pi over 180 radians per minute. So that boils down to pi on 9, or if you want to use a decimal, use plenty of decimal places. It's that in radians per minute. Okay, now because I want to go to kilometers per hour and I might need to use this, I'm also going to multiply it by 60 and go 20.95 9.44 radians per hour. Okay, so I'm looking ahead at the units that the answer needs. Okay, and perhaps I'll need to factor this in. Wink, wink. Now, also, the other thing is that we have an angle at this one given point in time. That angle is 55 degrees, and so we need to turn the 55 degrees. So theta into radians, we need to turn that theta equals 55 degrees into radians, and we times it by pi on 180 and 9599. So your calculator will provide that to you. That's in radians. Okay. So we've got an expression for d theta dt, and we've taken care of our units. And so what do we got to find? We've got to find the boat's velocity. Now that will be, as it goes along here, that'll be the rate of change of x displacement along there with regards to time. So we've already got d theta dt. Can we use that? Well, if we have something d theta, well, that has to be dx if you know the chain rule. Dx d theta times d theta dt will give us our answer. Now, to get dx d theta, we need a relationship between x and theta. In the triangle there, it's a right angle triangle, so tan theta equals x over 120. So x equals 120 tan theta. Rearranging. So after we've rearranged, I'm just going to, that was in meters, I'm just going to use it in kilometers. Okay, you'll see that before I converted that. So remember, the answer needs to be in kilometers per hour, so it's 0.12 tan theta kilometers. Okay. Now, we're going to look at the chain rule in a minute, but I might just change that to 12 hundredths, that 0.12, because you can see it's going to be fed into a fraction in a minute. Okay, so it's 12 hundredths tan theta, and that's in kilometers. So we have to find dx d theta now. Dx d theta. Now the derivative of tan, you might want to pause the video, but the derivative of tan theta is 1 on cos squared theta, or some people say sec, S-E-C. This video is assuming you don't know the reciprocal trig function. So pause the video. You might want to break tan theta into sine theta over cos theta and use the quotient rule as one possible way. This video is not going to go into that. That's for a different video that you might have seen already. So the derivative of tan theta is 1 on cos squared. You might need to pause the video and do that separately and come back. So using that result, we've got tan theta times, 1 on cos squared theta times 12 hundredths there. Alright, once we've taken the derivative, so we have 12 over 100 cos squared theta. Now we're ready to go back into the chain rule. So dx d theta is 12 over 100 cos squared theta times d theta dt, which we worked out up there was 20 point, if you look, sorry, that's times 20.944. If you just look back at your notes, you'll see that, and we multiply that together. Now we need to find it at that point where we have the angle equals the 0.9599 radians. So at 0.9559 radians, we sub that in, so we'll have 12 over 100. Now cos squared theta is cos theta all squared, remember, so we have cos of 0.9599 all squared, and that's times by the 20.944, which can go up there with the 12, and this should get it all in the right units, and we get 7.64 kilometers per hour.